Hello everyone, thanks again for joining us for DirectX Dev Day. My name is Michael Dougherty, and we are here to talk about Microsoft's HLSL compiler. HLSL is the standard GPU shading language. It's used by nearly all AAA games. We've spent significant time on the HLSL compiler. In fact, we have a new-ish compiler called DXC, and that's what I'm here to talk about today. So we'll be covering a few topics today. The first, we'll talk about DXC and what it provides and why we transitioned from the older compiler called FXC. Next, we'll do a deep dive into how to use DXC and its associated components for building game assets. And finally, we'll wrap things up with a few tips and tricks on how to use the compiler and a brief discussion of our roadmap. So as I'd mentioned, Microsoft has a newish compiler called DXC, and moving from an older compiler to a newer compiler can be difficult. Just want to be clear that the HLSL language itself hasn't changed, just our implementation of the compiler. So if you're familiar, the old compiler was called FXC. It had associated headers and libraries that folks would use to interface with the compiler. And an intermediate language called DXBC. I'll talk more about intermediate languages here in a minute if you don't know what they are. And then it also had a command line tool. FXC supported all the way up to shader model 5.1. And it's worth noting, again, I'll talk about intermediate language here in just a minute, but the modern drivers are converting your intermediate language from the old compiler to the intermediate language of the new compiler anyways today. So our new compiler is called DXC. It has a new set of headers and libs and a new intermediate language called DXL. And the newer compiler is required for supporting all of the latest things that we've exposed as part of HLSL, wave intrinsics, 16-bit types, which can run much faster than full 32-bit types, and then some really cool features like ray tracing, variable rate shading, etc. All of these are exposed in the new compiler. Another cool feature of the new compiler is it is open source and available on GitHub. So you can search HLSL GitHub, or I provided our URL directly to the compiler. It's a standard GitHub site. It has some great things for you to go investigate. There's the issues list where you can see where all of our bugs and current issues are, and you can also file a bug if you run into an issue, or you can even give us a suggestion on what you'd like to see. The documentation is also on the GitHub wiki. It has details on all of the newer shader models. It has usage notes on how to use the interfaces and how to drive the compiler. A port guide if you have FXC code and you're moving over to the new compiler, that we have a few tips and suggestions. Again, the language is the same. We've actually jumped through quite a few hoops to make sure that older shaders work with the new compiler, but there are a few issues that you might have to go fix up, and that's what the port guide is for. Another super cool thing that we have is releases. You no longer have to wait for the Windows SDK to come out once a year or every 6 months to get an update to the compiler. You can go to GitHub and download our latest release and use the latest and greatest much faster. So I think it's worth addressing why we actually moved to a new compiler code base. FXC was written at the time when we first started with shading languages. They were maybe 5 lines, 6 lines of code. And it was really kind of a very thin wrapper around an assembly language. Way back then, the GPUs were severely limited. Boy, we've grown over time. Shaders can now be thousands of lines of code. And shaders can also do very complex things. Like, for example, in ray tracing, we have shader libraries that are called. We really needed to move to a more mature compiler code base. So Microsoft adopted Clang and LVM, which is a very standard open source compiler infrastructure. And DXC uses that common tooling. The team has been working on it for several years, and there's quite a large team that is doing active development on DXC today. A few other nice things, because it is open source, we've had some industry partners add some things. SPURVGen is one of the things that have been added, so a lot of folks are using HLSL to generate their SPURV shaders now. It's also worth noting that on the Xbox family of consoles, DXC is now the standard compiler that we're using over there. So now I'd like to take a minute and discuss in detail how to use DXC and its associated interface called dxcompiler.dll. As many of you know, building shaders is often a lot more complicated than building, say, C++ source code. A lot of times the compiler is used as an output from an asset build engine or sometimes even art tools. And also, thousands of shaders can be compiled at one time, and so getting performance out of it is super important. So given the feedback that we've taken over the years for FXC, we have changed the interface for the new compiler to be a little more user-friendly. Three primary things that we've done to change the interface. The first is there is the interface to the DLL, which you can use to talk to the compiler with C++ code, and there's also the command line. And we have unified the way that you feed all of the flags and switches to the compiler between the command line and the DLL interface. That helps us write one piece of code that works for both paths, and it also allows us to document compiler flags and switches and controls in one way and be assured that it works for both when you're using the command line and also when you're using the DLL interface. Secondly, the shaders have grown. The PDB, which is the debug program database for debugging, and the reflection data have grown as well. And we used to store those kind of by default embedded in the shader, and now we don't do that. So the new compiler by default certainly stores PDBs separately, and it has the capability to store reflection data separately as well, hopefully significantly shrinking the size of shaders. Finally, when the shader compiles, it generates not only the intermediate language, but also some supplementary data, a shader hash, sometimes the root signature is embedded. And the old compiler, it was a little too difficult to get all those various subcomponents out of the compilation. And now we've changed the interface to where it's quite easy to compile a shader and then get all the various subcomponents directly out of it in one step. So I wanted to cover briefly, for folks not in the know, what the compilation flow looks like and discuss what an intermediate language is and how they're used. So the way that the compiler is used is you write source code in HLSL, and you use our compiler DXC, and the compiler will compile the source code into what's called an intermediate language. It is a short assembly-like representation of your code, and that is actually what we save when we compile a shader. Here I have a representation of the compiler saving your reflection data and your debug information separately. And then at runtime, when you that shader is handed to the GPU driver, and the GPU driver is going to take that and convert it into machine code that is specific for the GPU that you're running on. I'm going to go into each one of these recommendations in detail and talk about exactly why and some of the advanced features, but I'd like to just cover right up front what our recommendation is for using the compiler. We recommend that everyone compile a shader and they generate a PDB. Generating a PDB is easy. You enable debug information and then you give it a file name and it'll save that PDB out separately. And then we also recommend that most folks generate or save the reflection data that the compiler generates off into a separate file so it can be consumed later. And there's a few switches for that. So first, let's do that deep dive on shader symbols and what they're used for and how to generate them. So why would you generate shader symbols? Well, when you're using PIX, our tool for GPU debugging, you're going to want shader symbols so that when you go into the pipeline view and view a shader, your source code shows up. This allows you to edit that source code and modify it and run a few experiments. Also, you need source code for shader debugging. And then this is kind of non-intuitive, but PIX actually looks at the PDB and it uses it to understand how some buffers are formatted and information about your resource names. And if you have a PDB, then that will show up automatically in PIX, which is really convenient and nice to have. And our goal for shader symbols for HLSL is to make it as seamless as C++. It should essentially, when you compile a shader, it should generate a PDB. And then when you open up PIX, the shader has a small path to your PDB, and ideally it finds it right away. If not, well, then you can use the PIX UI to find your symbols. The other thing that PIX does, because it's often a common case to share PIX captures between other development team members or even Microsoft, PIX will actually gather up all the PDBs that you pointed it at and save it as part of the PIX file. That way they're not always external and it's easy to, again, share that PIX capture with other folks. So here's some more detailed instructions on how to generate and strip, PDBs. Again, ZI is the flag that you say it generates PDBs. And then you want to give us a file name, and the compiler will save the PDB out to that file name. Often it is the case that a machine is generating the shaders at asset cook time, or you just don't know. There is no single shader name that you have. So we have a convenience function here. If you give us, instead of FD file name, if you use FD and then give us a slash, then that tells the shader compiler to go ahead and generate a PDB name based off of the shader hash and save it out. So kind of a handy thing to have, so you don't, if you don't have a obvious name to call your shader, let's say your engine calls it 5649240, then you can just save the PDB out as a shader hash. If for some reason you do want to have the legacy behavior where your debug information is embedded or contained in the actual shader binary that we send to the driver, it's not our recommendation, but if you want to go back to that behavior, you can use the qembed debug flag to go back to the legacy behavior. Next, we'll talk about reflection. So one handy thing is the reflection API is defined in D3D12 shader.h, and it's wholly part of the compiler. It uses interfaces exposed by the compiler's DLL. You don't need the DirectX runtime or any of that complexity in order to use reflection. So it's kind of nice if you have an asset a build pipeline and you're trying to keep it as lean and as small and minimize dependencies as you can on it, then you can go that route and do all of your reflection without ever initializing or using DirectX. It is worth noting here that when you change compiler optimizations, it is possible that your reflection data will be different. So we try to keep 03, which is our most optimized build of a shader, to have the same resources as OD, but there are a couple specific cases where when we're not doing optimization, the resource requirements that you're going to see in reflection are going to be different. So it's something to keep in mind. So how you do reflection is very similar to how you generate PDBs. The flag is called -FRE, and then you give us a name of a file and we'll save your reflection data out to that file. I'll cover how to use that here in just a minute. It's worth noting that by default, we leave reflection embedded in the shader file. We do this so that we can match existing behavior. We have a lot of asset pipelines out there that expect the reflection to be saved as part of the shader, so we went ahead and left that there as a default. But you can simply do qstrip reflect, and that will keep the reflection data from being embedded in your shader and then saved to an external file. We're going to spend a few minutes walking through the interface to the compiler. This is going to be useful to folks who have are have code that is using the FXC interfaces, and they want to port their code over to using the new simplified DXC interface. Next, I'd like to share a few pages of source code which contain details on how to use the dxcompiler.dll interface. Getting started is really easy. You just include DXC API.h and then include our DXCompiler library. As I had mentioned, we are unifying the command line interface and the DLL interface. So for the DLL interface, the first thing I need is a list of arguments, which are going to look just like the arguments that I would send to the command line. So in this example, we have a simple vector of strings, which we're going to use for arguments. The first one is -e for entry point, which is main. The next is -t for target, pixel shader 6.0 in this example. Next, I'm going to ask the compiler to generate debug symbols with -zi, and I'm going to give it a path to those symbols with -fd and then the PDB path. It's worth noting that the DLL interface won't actually do the file I/O and save this PDB out, but we do expect you to provide a PDB path because that path is going to be stored in your shader object output that the compiler is going to generate, and PIX needs that so it's able to easily look up your PDB when you load a PIX capture. Next, we're asking the compiler here to please don't embed reflection in the output shader object and save it out to an external file called refpath -fr with the -fre flag. Lastly, we are doing, just for fun here, we're doing a define as an example. So -d is how you send the compiler a define. And in this example, my define equals 1. So the next thing we're doing here is we are creating an instance of the compiler. And then shortly after that, we are calling compile. We're taking this array of strings as our flags to the compiler, and we're going to compile the source, whatever, some text file that I'm compiling. And we have an include handler here. For folks who haven't used one of those before, when the compiler sees #include, it'll call this include handler back and ask you, hey, can I please have this file? And then it'll be your job as handling the include handler interface to give the compiler the files that it's asking for. It's important here that the result here is this result object. We're going to go into quite a bit of detail what that result object is. So after you call compile, you're going to get a result object back out. And the result object contains several different things. You can think of it as a kind of a bucket of results or things that you might get back from the compiler. Lots of good stuff here. The primary one obviously is the DXC out object. This is your shader output. It's the file that you're going to be sending to the driver at runtime so it can finish the compilation and run the code on your GPU. Also of interest is errors. If the compilation fails, you're going to want to take a look at the error string to see what went wrong. We went into great depth about the PDB, so that is one of the outputs. We've also talked to some respect about reflection. There's a few advanced things that you can also get out as output, depending on how you use the compiler. For pre-processing, it might actually be outputted HLSL for, you might get something advanced like the shader hash out of the output. So these are all available after you call compile. So after the compilation, we get our result objects. The next thing we do is check the status of the compilation. Much like the old compiler, it's after getting the status, it's often handy before exiting to look at errors. Even if the status isn't okay, we could have things, the compiler could tell us some errors. Common things for errors are syntax errors and things like that that you can get out of the compiler. So in this example, we check status, and then we get the output for errors, and if we see errors, we print them. And then at that point, if the compilation failed, we go ahead and exit. The next thing we're going to do here is, again, we have that results object, which is a big bucket of outputs, and this is the most common and interesting one, which is the DXC out object. This is our shader that we're going to send down to the driver, and in this example we're getting it as an output and we're writing it to a file. And here we are saving out the shader symbols. So again, we have our result object, and we're getting out the PDB out of the result object. It's important to note here that the PDB path from compiler is important. That's another thing that the result object will tell us. And this is the either we supplied the PDB name to the compiler or the compiler generated it automatically. Either way, we need to make sure that we save the PDB file out with that name so that Pix is able to find it later. And finally here, we're taking our result objects again, and we're asking it for the reflection output. In this specific example, we are using that reflection output directly. We're just grabbing, it's just a big buffer of data. And we're using the library utility interface to create a reflection interface for that data, and then using it directly. Obviously, you can, after you get the output, you can save it to a file and then open it up later and read those bits in and create a direct reflection interface directly from those bits as well. All right, next up, I'd like to share a few tips and tricks on using the compiler. We've talked a lot about strip data. I want to make sure we're clear on what strip data actually means. The flags that you can send to the compiler to say strip something, the debug information, the reflection, the root signature, if you're using private data to strip that out of the shader, those apply to the DXC output object, essentially the shader that you're going to send to the driver. Those apply only to the output object. The results part that is returned from the interface will still have all of that data available, so you can save it to an external file or do whatever you need with it. So again, we recommend that you strip everything and keep it out of the shader binary, because most likely you're going to throw it away, and then that way you're able to minimize the size of your shader binaries. So let's talk about multi-threading. Using the compiler in a thread-safe manner is super important. We understand that performance for the compiler is critical, especially when you're compiling thousands of shaders as part of a asset pipeline, and you don't want to wait hours in order to cook your level. And so when it comes to using the compiler in a thread-safe manner, the simplest way I can explain it is you want to create one instance of the compiler per thread, and then you want to start and complete the compilation on the same thread. So a more concise way to say it is the call to DXC create instance in order to generate the multiple instances of the compiler is thread safe. But the objects, primarily the compiler interface created, isn't thread safe. So again, please do create a single compiler object for each thread and use it on that thread. And also for include handlers, if you're supplying a custom include handler, which many folks do, you have to make sure and recognize that that include handler needs to be also a separate entrance per thread, or it needs to be thread safe. And again, what you absolutely don't want to do is create one compiler instance and then start calling it from multiple threads. That's an absolute no-no. We have on GitHub in our wiki, there is a document using dxc.exe and dxcompiler.dll, which goes into lots of detail about thread safety and also includes several code examples for you. Now I'd like to briefly talk about our languages and features roadmap. So on our roadmap for the short term is shader model 6.6. There will be a new shader model. Unfortunately today we are not ready to talk about the details of that just yet. I know everyone wants to know what the next new set of hardware features are, but we are still working with our hardware partners on defining what shader model 6.6 looks like. So stay tuned for that. The next thing is reflection data that the compiler is generating today is much larger than we would like. Not to get too technical, but it's a subset of the DXL and it's not very compressed. So here very shortly there will be a release of the compiler where the size on disk of the reflection data will be much, much smaller. And if you need to ship reflection data as part of your shaders, this will help your size on disk dramatically. Next, there are a few advanced inputs to the shader compiler, root signatures or private data as an example, that aren't really supported by the new interface. And how we're going to handle that is the command line. You can supply these arguments as additional files that we will include in the shader object output. For the DLL interface, we're actually going to handle them in the include handler, where if you supply file names on the string arguments to the DX compiler DLL, we will ask the include handler for you to supply those files, and then we will bundle them up as part of your shader object. So kind of a neat way to add some of the more advanced inputs to the new interface. And finally, we are always evolving the language, and this is just for the short term. We have much more advanced things to be adding in the long term, but for the short term, we're looking at bit fields, and we're also looking at supporting the offset of operator and also more complete support of size of. So that's just happening in the short term. And there we go. Thanks for spending a little bit of time with me on HLSL. A few folks to thank here. Obviously, there's my team, the HLSL Compiler team, and the rest of the Microsoft teams at DirectX, DirectXML, and Pix, and the Xbox Graphics team. Also, big shout out to David Cook and the Microsoft HEG team. David did these original slides, which have been modified slightly for today. Also, a huge thank you to the Clang and LVM development communities. And I'd also like to call out both Google and NVIDIA. Both have spent significant time in our code base and have made significant contributions. So big thanks to them. And finally, I'd like to thank customers. That's you guys here working on games and trying to get things shipped. Appreciate all of your bug reports and suggestions and patience with us. And that's it for me. Thank you.